Well, hello, here we are again. We're going to be looking at some ordered pairs here on this starter, and we're wondering if you can tell what the heck is going on between each of these ordered pairs. And then which one doesn't belong based on that. So we've been talking about translations, rotations, reflections, and dilations. And remember, the dilations are most new transformation, is that the way to say it? Where you multiply by a scale factor to make a shape bigger. If the scale factor is bigger than 1 and you multiply by a scale factor smaller than 1, like 1/2 or 1/4 or 1/5, something smaller than 1, that makes the shape smaller. All right, so let's take a look what we got here at all these ordered pairs. You should be trying this one out on your own, number 8 on your starter, and this will be turned in. Just listen to the directions on when you'll turn those starters in, okay? So I'll be looking down here at my handy dandy iPad here. That's where I'm doing my lessons and all my writing. And I'm hoping that you guys can follow along. If I'm looking down, you know what I'm writing, okay? So here we are. How do we go from 3-2 to 6-4? Well, there are a couple of ways. We could add 3 to the x's, and then we could add 2 to the y's, but that would be a translation up and to the right. So that, I mean, all these could be written as translations. So let's get a little bit more specific here. Well, what is in common between 3 and 6, as well as 2 and 4? Is there something I could do to both of those numbers, but the same thing, like multiplying by 2? So let's check that out really quick. If we multiply 3 by 2, we get 6. And if we multiply 2 by 2, we get 4. So this could be a dilation, right? With a scale factor. Ooh. A dilation of scale factor 2, or we could say k, because we've been using k for scale factor. Also here on B, you'll notice, how can we go from -1 to -2? Well, we can multiply by 2, and -5 to -10, we could also multiply by 2. So again, this could be another dilation with a scale factor of 2. 4/7 to 10/4, this is C here. I'm not saying C is the answer. Let me get rid of that, because you might think that, right? Going from 4/7 to 10/13, I'm not seeing a multiplication. We can try to see, right? Here's one way you can try to see if there is a scale factor. How do we go from 4 to 10 by multiplying? Well, take the new and divide it by the original, yeah? So the new would be the 10. We're going to divide by 4, and that would reduce to 5/2, or 2.5. And then doing the y value, going from 7 to 13, the new is 13 divided by 7. Well, that doesn't reduce. So these actually aren't a scale factor, because we're not going to from the original to the new, the same way by multiplying, right? So this can't be a dilation. This one has to be something else. So maybe we'll come back to that. If you notice here, though, going from 7 to 14 and 7 to 14, again, that could be multiplying by 2, and therefore is also a dilation of scale factor 2. And so we already know that C is going to be out because it's not a dilation. We could easily eliminate that. So honestly, for this one, it looks like it's really just adding 6 and adding 6. And maybe someone oopsed and was supposed to multiply by 6. I'm not sure. But that's how I see this one. Maybe you saw it differently. It's not that you have to go and rewrite your whole answer. Maybe you're not wrong. Maybe you noticed something else, right? Well, I chose B because it has negatives in it. Well, you're not wrong, right? That's a reason for why that one wouldn't belong. However, there is something more contextual to what we're doing now in class, like dilations, okay? Everything has a dilation of scale factor 2, except for C, which doesn't have a scale factor at all because it's not a dilation. So we're going to continue. We're going to be describing sequences of transformations involving dilations now through each of these problems. And each time I hit a new slide, I'm going to look at you, and I'm going to say, I want you to try it, because we've progressed through this, right? This is session 3 of this whole lesson 5. So we should be able to get somewhere on these by ourselves. So try it. For the challenge of the week, Ryan's teacher draws figures A, B, C, D, and E, F, G, H on a coordinate plane, as you can see here. That's that blue and red shape there. The challenge here is to show that the two figures are similar using 3 or fewer, so you can use 2 or 1 transformations. What is one sequence of transformations that Ryan could use. Now, I don't care if you're going from blue to red or red to blue, as long as you can show you can go from one to the other, then you can show that they are similar. Obviously, these can't be congruent because they are not the same size. They are the same shape, but not the same size. Are you ready? Here are a couple. You should have tried it. That's what I'm saying. Pause, because that's a button, and I know you're able to use it, and try this one out. So here is one possibility, and it's not the only possibility. I'll talk about how actually I thought about it prior to what your text is actually saying. This is saying to reflect, then dilate. So what they're doing is they're taking the shape, let me do this here real quick. They're taking the shape A, B, C, D. They're going to reflect it first, which reflects it down to here. They're reflecting it over the x-axis, so this becomes a reflection down here. So it just flips down there. They're saying a reflection again, which is actually over the y-axis. So this shape right here is reflecting over to here. And then this part of the shape is reflecting to here. So the first time it reflected over the x-axis, it reflected down here into quadrants 3 and 4. And then this reflected over the y-axis, bringing everything on the right over to the left and everything on the left over to the right. So this is where we're at now. And then they used a dilation, which is exactly what we see here. They're taking a side length 2 and going to 1. So this would have to be a scale factor of 1/2, right? They're taking this side length 2, 4, 6 and going to a side length of 3. This is like 2 diagonals, and this is 1 diagonal. This is a length of 4, and this is a length of 2. Also, you'll notice that the distance between the shape and the x-axis is being cut in half from 2 to 1 right here. So that definitely does work that way. And that did use 3 or fewer. The way I saw it actually was taking A, B, C, D. Let me see if I can just show this. And rotating it around the origin 180 degrees. So it'll keep the same distance from the origin, but it would put it 2 away here, right? Which kind of left us with what we had here after the second reflection. And then we can dilate by a scale factor of 1/2, just like I showed. So I was thinking rotate 180, which if you haven't noticed yet, a rotation of 180 degrees is a X reflection, Y reflection. But that does get us there too as well. Maybe you got there some other way. As long as it was 3 or less, then you did a good job. The book also goes into like looking at the ordered pairs. Looking at the ordered pairs and trying to picture what's going on is a little difficult, but you might be able to do some math, whether it's through dilations or all the rules we've learned, to go from A, B, C, D to E, F, G, H. In this case, this is a rotation like I did, and then the dilation. Number 6, the vertices of a triangle ABC, which is not graphed here. We have A double prime, B double prime, and C double prime, is shown here at the right. The sequence of the transformations of the triangle ABC results in A double, B double, and C double prime. Which of these A, B, C, or D would get us from ABC to this A double prime, B double prime, C double prime? So what I did is I actually plotted these points. It says that all our actual original triangle is right here, right? So 4, 8, 8, 0, and negative 8, 4. And I went and prepared this beforehand because I didn't want to take up too much of your time. I'm going to place A at 4, 8, which is right here. Right? Oh, that's 3, 8. Let me move over one more time. There we go. I need new glasses, apparently. So that is where ABC is. Obviously, there has to be a dilation in here. If we're going from ABC to A double prime, B double prime, and C double prime, we're also getting smaller. So what does that tell us about the scale factor? Remember, when we're going smaller, our scale factor has to be a fraction or a decimal that is less than 1. Obviously, it has to be greater than 0, but we're just saying less than 1 because it has to be somewhere between 0 and 1. Now, I want you to look through A, B, C, and D and maybe take a guess at what, or maybe do some elimination as to what is and is not going to work here. All right, hopefully you've got a guess down. Don't cheat. It's not good for your brain. Our first one says to rotate 90 degrees clockwise and then to dilate by a scale factor of 4. Well, that should have been our first red flag. A scale factor of 4 would make the image larger. But remember, we are going from the larger triangle to the smaller triangle here. So it should be a scale factor less than 1. So all of a sudden, I don't even have to do the 90 degree clockwise because I know this dilation is out. If you look at the second one, the dilation of the scale factor of 4 again pops up. So that one is out for the same reason. Now, scale factor 1/4 and scale factor 1/4 are both probably going to be okay. Now we need to start talking about rotating. If I rotate, like C says, clockwise 90 degrees around the origin, I'm going to find one point on mine and start rotating it. If I go clockwise 90 degrees, this point would go to here, right? This point right here, C, would end up somewhere over here, and A would end up somewhere over here, right? And you can do all those rules to figure that out. If I rotate that here and I do 90 degrees, and I place B where it's supposed to be, this is not going to dilate to where ABC is right now, or A double prime, B double prime, C double prime is. I can make this smaller by dilating it, but I won't be able to get this to fit on top of this triangle right here, right? Let me clean this up just a smidge. And let's go try the next one. I mean, we just eliminated C, so the answer is, well, we eliminated everything. If this were a test, honestly, I would have just picked D and moved on without even trying, but I want to show you guys how it works. Let's try counterclockwise. If we take ABC here and I go counterclockwise 90, right? Let's see, that's going to put B right up there because it was at 8, 0, so it's going to go to 0, let me draw this in. That's going to rotate up this way. And we can see here now we're in the same orientation, and the scale factor is going to work for 1/4. You don't actually have to go find that, but we know that it has to get smaller, and that's my only other option anyway. All right, kind of the same thing here with a rectangle. We're going to go from JKLM to the double prime JKLM. Pilar draws this rectangle, right, the blue one, and she performs 2 transformations. That's why there's double primes on there to form that. What 2 transformations could they be? Again, there could be multiple answers here, and I'm fine with any of those as long as they work. Go ahead and try it out. All right, and then the second part of this is, could we have done that in reverse order and still made it work? So let me show you what I'm thinking is going on here. I'm noticing that both of these shapes are 2 away from the x-axis. Okay, see how this is 2 away here and 2 away here? I mean, I already know a dilation has to occur, but if I do a dilation on JKLM right now, it's going to move it closer to the origin. So I'm going to have to probably translate or something. I can't necessarily reflect yet. I'm not seeing that happen. So what I'm going to do is I'm going to take JKLM and figure out what I have to dilate by and see what happens from there. I'm going to do new over old to figure out what that dilation is. The new side here is 2. The old side, or the original side, sorry, is 4, which reduces to 1/2. And I'm just going to make sure that works. 1, 2, 3, 4, 5, 6 times 1/2 is 3, so it does work for my other sides. So my scale factor is 1/2. If I multiply everything by 1/2, let me show you what I'm doing there. 6 times 1/2 would give me 3, so that's going to be one side. 4 times 1/2 is going to give me 2, and that's going to get me this rectangle right here. But it's not going to stay right there because I'm going to dilate it about the origin, or toward the origin in this case, which means that my distance from my x-axis and my y-axis is also going to be dilated by a scale factor of 1/2. Well, those distances are 2, and because the distances are 2, multiplying that by 1/2 means that those distances are going to be 1. So that's going to move this in closer, up 1, and this over 1. Let me move that out of the way there. Now from here, so that's a dilate by 1/2 around the origin, like so. And then, well, I can't reflect because the distance here is not the same here. So I'm going to, also if I reflected, keep in mind that this is J prime now. This is K prime right here. This is L prime, and this is M prime. So if I even reflected, that means that my M would have to go up to here if it reflected. So that wouldn't keep everything in the same orientation. So I'm going to translate everything up 1, 2, 3, 4, 5. So translate up 5 units. I'm just going to put T here. for translate, hopefully you guys can understand that by listening, right? So what if we did this backwards? What if we went translate and then dilate? Well, let's see what that did, and we'll answer that second question and move on. If we translated up 5 first, oops, got something in my way there. We went 1, 2, 3, 4, 5, and then we dilated. That's not gonna work. Let me show you what that would do, okay? Again, we'd still have that same size box, right? A 2 by 3 box. But when I dilated this, we're not gonna go up this way. Remember that when we dilate from the origin, we're actually going to get closer to the origin. So this point right, let me see if I can do that. This point right here, which is at 2, 3. This gets interesting. 2, 3. Well, the 2 divided by 2, or 2 times 1/2, would get me here, and then 3 divided by 2, or 3 times 1/2, would get me down to 1.5. So it actually dilate to there, which is really strange, and it doesn't work, right? We should be getting closer to the origin. So no, we can't do it in reverse order. All right, here we are practicing again. Your turn. Can you map PQR onto LMM? So take PQR and do some transformations. Translate, reflect, rotate, and dilate. You're going to have to dilate because it's getting bigger here. And go ahead and try that. Okay, then. So describe it. All right, well, let's go here. We're going to go from PQR, like so. Let's see here. I'm gonna try dilating first. Is that okay? Let's dilate this out to be a bigger shape. It looks like this side right here, NL, corresponds to RP, or PR corresponds to LN, however you want to say that, but order does matter. So we're going from 2 to 4. The new shape is a size of 4. The original is 2, so our scale factor is going to be 2. You can also see that here and here. We have a side length of 8 over its corresponding side. From the original is 4, so the scale factor is most definitely 2. Let's see what we can do there. We're going to multiply by 2, and I'm going to do it around the origin, I guess. Let's do it around the origin. So 1, 2. If we dilate that point by point, multiplying both of those by 2 gives me 2, 4. Which is going to take me off my grid, it looks like. So 1, 4 here. Multiplying both of those by 2 is going to take me to 2, 8. And 2, 8 is going to be 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be about right there. Sorry, I went, yep, 2, 8 right there. That's right. I lost track there. And then lastly, we have right here is 5, 4. 5, 4 times 2 is going to take me to 10, 8. 10, 8 would be on the same y level. So dilating by a scale factor of 2 takes me way up here. All right. Hopefully you guys see that. I'm going to get a different color really quick so I can start moving that around. And then looks like they're lined up, so I could probably translate down 3. 1, 2, 3, 4. Translate down 4. So we have a dilate by 2. Translate down by 4. And then a reflection over the x-axis, which would reflect, that point would not reflect, this point right here would reflect to here, to L, and right here would reflect to M. So, okay, dilate by 2. That works. We had to translate down by, what was it, 4? 1, 2, 3, 4. Down by 4 units, and then we had to reflect across the x-axis, right? So that should all be written down, or maybe you got there differently. If you actually showed that the bigger triangle went down to the smaller triangle, you're still showing they're similar, but the question specifically asks, how do we map PQR to LMN? So that's why I went that route. All right, just a couple more slides, guys. We're almost done. We're a little ways in. I apologize. Nota draws the figure X in the coordinate plane, as shown. Then he performs a sequence of transformations on X to figure Y. So we're going to go from X, excuse me, I got the hiccups all of a sudden, to Y. What sequence of transformations could Nota have performed to map figure X onto figure Y? And once you find one there, can you find another one? Try it out. What I'm thinking is we take X here and we rotate it around the origin on 180 degrees, and a square will rotate to a square. In this case, it would put it, oh, that's not what I'm grabbing. There we go, to here. But I can't just do that. So that's a rotation of 180 degrees, whether that's clockwise or counterclockwise. And then I'm going to dilate that by a scale factor of 1/2. What that's going to do is we're going to multiply this side and this side by 1/2, which are the same. And that's a 4/4, which will be multiplied by 1/2, which will get down to a 2/2. And since the origin is on the shape, that point doesn't move, so I can just leave it there. So again, rotate 180, and then a dilate by 1/2. And then part B, is there another way? Well, I talked about it earlier. Anytime you do a 180-degree rotation, that's the same thing as a reflect. So you could reflect this image across the x-axis, and then you can reflect it across the y-axis, and then dilate by 1/2. You also could have went across, reflected across the y-axis, then across the x-axis, and then dilated. You could have translated down 4, left 4, then dilated, or left 4, down 4, then dilated. You could have dilated first, right? You could have got your little 2x2 first, and then translated, or rotated 180, right? There's lots of ways to actually do this. All right, lastly, which sequence of transformations could map A onto B? Well, let's find out here. Go ahead and pause the video and finish this one up for our last problem here. Okay, let's check out A. Going from A to B, a 90 degrees clockwise rotation around the origin. Let's see where that takes us to. Clockwise around the origin. 2, 2 would then go to negative, or 2, -2. Followed by a translation to the left. Well, no. Well, first off, anything that doesn't have a dilation in its description isn't going to work, right? Because a dilation makes it smaller or bigger, and we need to get smaller. So this one doesn't even have a dilation in it. The first one here says a dilation. Why did that draw and not do this? There we go. It says a dilation, doesn't give us any scale factors in this. A dilation with a center of dilation at the origin, followed by a translation down and a translation left. Well, if we dilate it small enough toward the origin, and then translate down enough, and then to the left enough, that would work, right? So this is not being too specific, but that would work, right? What about a reflection across the x-axis? Go put this back over here so I can get the right size, sorry. A reflection across the x-axis would put us here, followed by a dilation around the center at the origin. Well, if it was a small enough dilation, we'd be about here. Oh, and then we get closer. And then translating left. Ooh, no. Now, here's the thing. If you forgot that dilations don't, like, they do move you closer to the origin as well, and we left it where I just put it, then you would think that translating to the left would work. However, but because we dilate by 1/2, that also dilates our distance to the origin by 1/2. So moving to the left will not work here. This one's close, but tricky. All right, what about, I'm cleaning this up now. It's got to go. What about a reflection across the y-axis followed by a translation down and a dilation? Well, I think so. So if we reflect across the y-axis, again, I'm doing a quick sketch here to show it. That would put the rectangle about here. And then translating down and a dilation. Oh, you know what? It's not going to work. Because even if I go here, if I dilate, that's going to bring me in closer to the origin, right? So I'd have to be more like here for the dilation to work. So a reflection and then any type of translation, that's not going to work because wherever I put this thing, it's going to bring me into the y-axis as well as closer to the x-axis as well. So that's not going to work. That one's also a tricky one. That one also actually almost fooled me right there. All right. A 180-degree rotation around the origin. Get off my screen. Not you. You would put me here. And then followed by a dilation with a center of dilation at the origin. So we're going to do the correct one here. We're going to go down to a little 3x2. Hopefully I can get this the right size. Boop. So we get it the right size, but remember that that distance also shrinks us in. And then it says translate down and to the left. That one works. Woo, that one's tricky too. So hopefully that kind of made sense. Make sure you guys are checking all your homework. You can check those grades that are posted up in our classes. And if you're a rando watching this on YouTube somewhere, welcome to my class. I'm Mr. Nelson. Mr. Craig greets you as well. But make sure you're doing your homework. Check that out. Make sure you know what you're doing today. And get your work done, guys. Stop falling behind. It's not good. The end of quarter is going to come and you'll be like, Mr. Nelson, what am I doing for my grade? And I'm going to look at you and I'm going to say, go back in time and do your homework. Okay, cool. Well, we'll catch y'all later. I hope you enjoyed it. I did. Peace out.